Welcome one and all to another exciting AP Stats Day. Today we're going to do problem set 14.1. All right, so here's our first problem, an extinct beast. So we've got 2 bones, we have 5 fossil specimens. So there's our N, 5. And rather than looking at the data, they decided to just give me the computer printout. And this is very common on the AP Stats test to just give the printout when you're doing inference on regression. Okay, what's the equation of the least squares regression line? Okay, that's pretty simple. So you just have to be able to read the printout. This number right here, negative 3.6, that is your intercept, your y-intercept. And then this number right down here is your slope. So the equation of our line is going to be negative 3.6596 plus 1.1969x. Pretty simple. All right, letter B. We left out the t statistic for the hypothesis test. Again, the null hypothesis will always be that the true slope, beta, is 0, meaning there's no relationship, which is what we always say null is, right? Nothing here, no relationship. Okay, so use the output to find t. All right, so you can see the t right here is missing. There is a t-value. A lot of students will misinterpret. We really don't use this or this or this from the printout because we're not going to be doing inference on the intercept. We only do inference on the slope. Okay, so we don't use those 3 numbers. So they did leave out the t and the p-value that we actually use and need. But no big deal. Hopefully, you know that to find t, all you have to do is take the statistic for slope, right? B, not beta, because we don't have beta. And then we're going to divide that by the standard error of B, okay? And those 2 values are given in the printout. So in this case, t will equal 1.1969 divided by 0.0751. All right. And there's our t, 15.94 approximately. Whoops, 15.94. Okay, pretty large t. All right, letter C, what's the degree of freedom here? Well, we had 5 fossil specimens. Now, this is tricky. The degree of freedom here is n minus 2, right? So the degree of freedom for this test is n minus 2 because we have 2 variable data. That's why, instead of 1 variable data that we've been working with previously. So in this case, our degree of freedom would be 5 minus 2 or 3. Okay. Use table C to approximate the p-value. So let's find table C. There we go. I think we have it as table B, but whatever. Degree of freedom of 3, and our t is off the table. So we know our p-value is less than this last entry. Okay, so our p-value is less than 0.0005. And that's the best we can do with our table. But guess what? It's good enough. Tells me it's pretty darn rare, right? A very small p-value. So very strong evidence to reject the null hypothesis of no relationship and therefore accept that there is a relationship. Okay. D, write a sentence to describe your conclusions. Well, that's kind of what I just said, right? letter D. With a p-value less than 0.0005, we have very strong evidence to conclude that the true slope is greater than 0. Okay, in other words, meaning that there is a relationship between these two bones. Not a surprise, really. Okay, letter E, determine a 99% confidence interval for the true slope of the regression line. Okay, so again, we start with our statistic for slope, which was 1.1969, plus or minus. We got to get our T star. Okay, our T star has 3 degrees of freedom, and we want 99%. Okay, so 3 degrees of freedom, 99% looks like right over here. Okay. 5.841. Okay, and then that needs to be multiplied by our standard error. And there's our confidence interval. So don't forget our conclusion. We are, was it 99%? Yeah, 99% confident. The true slope of the regression equation is between, okay, work that out. And let's see, I'm getting 0.7579 and 1.6359. And put units on that. I forget what the units are. Inches, something like that. Doesn't really say. Okay, but yeah, I don't see it. We'd have to go back to page 786 to find the units. All right, there we go. Let's try the next problem. All right, back to our jet skis data that we did way back in chapter 3. Again, chapter 14 obviously really lines up with chapter 3 because that's when we first did linear regression, and this is inference on linear regression. So a lot of teachers actually and the College Board kind of put those two chapters together. But anyway, I left them separate. Okay, formulate null and alternative hypothesis about the slope of the true regression line. State a one-sided alternative. Okay, so this is number of jet skis and fatalities. So the null hypothesis is nothing here, no relationship, right? Oops, sorry, can't see it. There we are. In other words, beta is 0. More jet skis doesn't change the fatalities, okay? Alternative, though, okay, more jet skis will increase our fatalities. Okay. All right, letter B. What conditions are necessary in order to perform a significance test? All right, so we need independence. And the data set, where is the data set? Page 125. Let's see here. Okay, so here's the data set. Okay. So we need independent random data. Well, this is really not independent random data. It's consecutive years, right? So we're technically not passing that requirement, but we'll still do the problem, as we always will. Just realize that could be a problem in making our conclusion. Okay. We also need to see that the true relationship is linear. So I'm going to go ahead and graph the data set. I think I have it in my list 1 and list 2 already. So there's our graph. Is that true relationship linear? Could be. Let's go ahead and do a quick linear regression on that. And a pretty strong R. Okay, I'll regraph it with that line. Okay. Now, I'd like to make a residual plot, but I've actually used like every list in my calculator. So go ahead and do a regression plot at this point, linear regression, and see if there's a pattern, right? If we have random scatter. Okay, if we have random scatter, then we'll say, yeah, true relationship is linear, right? If we see a curved pattern, then we'll go, looks like the true relationship isn't linear. So go ahead and do that on your own. It does look like we might have a little increasing spread about the line over here, right? That's a potential problem. Okay, because remember, we need the spread about the line to remain consistent throughout. Okay, and we also need the response, the y variable, to vary normally for every input, for every x value. So after you do your residual plot, then also do a normal probability plot of your residuals and make sure that looks fairly normal, or in other words, fairly linear. Right? That's how we check for normality on a normal probability plot. So anyway, there we go. I'll let you handle those checks. And I said them all rather than writing them, so I'm just going to move on. Letter C. Let's do the t-test. So stat, go to test, and towards the bottom, if you have the 84 plus, you'll see the linear regression t-test. And I want list 1 for x, list 2 for y, and we should want a one-sided alternative. And there's our t. Our degree of freedom is 8. There's our p-value, and if you scroll down, there's your intercept and slope. Also gives you s, r, and r squared. Notice, though, it doesn't give you the standard error about the line. It just gives you s. So if you wanted the standard error about the line, you go back and use this formula, because it does give you t and b, right? So you would use the t and b that it gave you to get the standard error of the slope of the line. Sorry. Okay. All right. So with our p-value, where did it go? There it is. 0. We have extremely strong evidence. To conclude that more jet skis in use results in more, what were we talking here, accidents or fatalities. In other words, to conclude that the slope is greater than 0. We have a positive correlation here, right? Remember, if I'm saying that my slope is greater than 0, I'm saying that my correlation is positive, right? Those are, and that's really what we're interested in. We're saying there's a positive correlation here, right? More jet skis in use, more fatalities from jet skis, which makes perfect sense. That's why our p-value is so small, right? If we didn't use any jet skis, it'd be pretty tough to have jet ski fatalities, wouldn't it? All right, letter D, determine a 98% confidence interval. So again, I'll just use my calculator since I have the data in there. So linear regression T interval. And there we go. And there's my interval. Again, notice these are in scientific notation. Okay. We should write, of course, a conclusion there. So let's do that. We are 98% confident. The true slope of the regression line is between, what do we have here? 0.027 and, oh, not 7. I'm looking, that was the B value. Sorry about that. It should be 4. And 0.1239. Okay, more fatalities. Per jet ski added. Okay, so in other words, every time we add one more jet ski to the number of jet skis in use, we would expect that many more fatalities. Notice it's very small because there's lots and lots of jet skis in use, but not that many fatalities. But there's a very strong relationship here that more jet skis will increase the number of fatalities, which makes perfect sense. Okay, next problem. Is wine good for your heart? Again, back in chapter 3, we originally did this problem, but back then we didn't know how to do inference on it. So let's take a look. Page 183 gives the data set, and here it is. So the number of liters of wine ingested per year per person on average, and then the heart disease death rate per 100,000, right? So there's my data set. Too many things at once. All right, letter A, is there statistically significant evidence of a negative association between wine consumption and heart disease deaths? Pick up my paper that fell on the floor. All right, try that again. So the null hypothesis, there's nothing here, right? More wine doesn't do anything. Alternative, and this is what's funny because for years, people would think that increased alcohol consumption, that has a negative impact, right? But people researched it for a while and started to say, whoa, this data keeps pointing in the exact opposite direction. And so now we're at that point where we're saying we think the true slope might be, less than 0, meaning more wine More wine will decrease the likelihood of death by heart attack. Okay. All right. So I've already entered that data in, I think, my list 3 and list 4. Okay. So before you do the test, I know a ton of students just love to jump straight to the test. And here's my p-value and here's my conclusion. But you need to make sure that you're not performing linear regression t-tests on things that aren't linear. So bare minimum, always do a scatter plot. And at least make sure that it's looking pretty linear. Okay. And you might recall this. We did this, I think, on one of the quizzes from chapter 3. And sure enough, I do see a negative association. And good idea, again, to just go ahead and do a residual plot. So I'll let you do that. So go ahead and calculate the best fit line. Well, I'll calculate the best fit line real quick. So this was list 3, list 4, right? And And then go ahead and do your residuals, make your residual plot, make sure it's not curved. Watch out for increasing or decreasing spread, and also do a normal probability plot of those residuals and make sure that the data is responding normally for each x value. All right, so this looks fine to me, so I will assume that we also pass those other checks. And don't ever write that, by the way. I'm just doing that because, again, I have limited space in my calculator here. So let's go ahead and do our test. This is list 3 and list 4. And we're one-sided with a less than. So a negative correlation. And we go ahead and calculate, and there is our t, and our p-value is quite small, 17 degrees of freedom. Okay, so our conclusion is with a p-value of, again, scientific notation, so 0.1. Extremely strong, exceedingly strong, very strong, whatever you want to go with. To conclude, drinking more wine will lower the rate of, I think it was death by heart attack as opposed to just number of heart attacks. And there we go. Letter B, find a 95% confidence interval for the true slope. So again, and this is the thing, at this point, most of the time, they're not going to ask you to show a ton of work here. As a matter of fact, most of the time they give you the printout on the AP Stats test. So I'm just going to go ahead and jam it in here, 95%. And there we go. So we're 95% confident the true slope is between -30 and -15.5. -30.5 and -15.5. Okay, so true slope of the regression line is between -30.5 and -15.5. deaths by heart attack per 100,000 per liter of wine consumed, something like that. I think it was liters of wine consumed. And there we go. Again, if you needed to show the work here, it's pretty simple, right? There's your B, so you put that plus or minus, and then you go look up your critical T for 17 degrees of freedom, right? And you get your standard error. Again, you're going to use the S they gave you and the T that you get when we just did the linear regression t-test, right, to get the standard error of the slope. Okay, so that's how you would show the work if you need to. All right, next one. Does fast driving waste fuel? Okay, again, back to chapter 3, page 129. Okay, that is right here. Right, so you might recall that doing that problem on a homework set. So I've entered that data in my calculator again. And this one really proves the point that I mentioned earlier. Don't just go straight to the t-test. I mean, sometimes the t-test won't mislead you, right? A lot of times it won't. But in this case, graph it first. So, as always, graph it first, actually. Not just this case. So there's the data, list 5 and list 6. And sure enough, you see, hey, get rid of the line I have there. See, hey, this doesn't look linear. It looks very curved. Okay. Now, since it actually starts curving back up, right, we're probably going to get a large-ish p-value. But if we had cut the data set off somewhere, right, and it was still very curved, you would get a small p-value, right? The reason we won't get a small p-value here is because it actually starts, it changes direction and has plenty of data on both sides of the curve, right? If it's just, say, like an exponential decay, you'll get a small p-value on that, right? Or if it's just exponential growth, you would get a small p-value on that, even though it's not appropriate, really, to be doing linear regression on something that's curved. So anyway, that's why you always look at it first. Okay, is there evidence of a straight line dependence between speed and fuel? Make a scatter plot and use it to explain the result of their test. So they do want me to conduct the test, but it's really the scatter plot already answers all the questions. But let's do the test. So, oops, test. I think I had list 5, list 6, and do two-sided. And there's our t. It's negative 0.6, so p-value is very, very large, as we already noticed from the graph. So we do have a really strong relationship in the graph. It's just not linear, okay? So I'm not going to write any of that. I think I've explained it well enough for you. Okay, 14.10. Again, this is the more typical way to get one of these problems. We have a printout. Okay, wow, notice that R squared, really strong. All right, letter A. Oh, this is actually, let's go back. We're talking about a runner's speed and the number of steps they take per second, which makes sense. If you're jogging, right, you're not taking that many steps per second. As you start going faster and faster, you're taking more steps per second. So we would expect a positive slope here. Letter A, how can you tell from the output, even without the scatter plot, that there's a very strong straight line relationship between running speed and steps per second? Well, that's jumping out at me. It already noticed that right out of the gates. R squared is really, really, really strong. And then there's also one other thing that you should check. Your p-value is very, very small. So it appears that there's a high, don't confuse the two, by the way. The p-value tells me there's a high probability that I have a positive slope here. Very high probability the true slope is positive. And then that tells me that there's very little variation about that regression line, right? So you can have a small p-value and not have a super strong R-squared. It happens, okay? So please understand, that's why we give both. They don't both tell you the same thing. They each tell something different. All right, so I guess I'll write this one, 14.10. Okay, so the small p-value and the strong R-squared. Remember R-squared, by the way, coefficient of determination. Strong coefficient of determination. Okay, letter B. What parameter in the regression model gives the rate at which steps per second increase as running speed increases? Okay, that would be the slope right here. Give a 99% confidence interval for the slope or the rate. Okay, so how about I'll show the work on this one. We would do 0.08 blah, 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 plus or minus 99%, 5 degrees of freedom. Okay, 5 degrees of freedom. Again, 99% takes me to this one-sided P, right? That, when you double it, right, because it's a confidence interval, 2 tails, this is single tail, that's 98%. That one there's the 99%. So 4.032. Okay, and that gets multiplied by the standard error of the slope, which is right there. Standard error of the coefficient, right? So 0.0016. It's kind of funny. The printouts give you the standard error of the slope, but your calculator doesn't, right? Your calculator gives you the standard error of the line. So it's kind of interesting how that works. But all you need is one of the two, and you can use it to, along with the T and the B to calculate the other. All right. So work that out. We do 99%, I believe, yeah. And there we go. We're 99% confident. The true slope of the regression line is between I did something wrong there. I used the wrong list. Yeah, this doesn't match up what I got on my calculator. I must have used the wrong list. Let's try that again. Oh, yeah. I don't have that in list 5 and 6, do I? Yeah, I don't even have that data. Whoops. So I have to do it by hand. So let's do that by hand. Yeah, forgot. I don't have the data, right? We're doing this off of the printout. So go ahead and punch this in there and see what we get. Looks like 0.07 to 0.09, roughly. And this was increasing, was it feet per second, I think? Feet per second per, I think it was number of steps per second as well. Yeah, per steps per second. A lot of pers there. There we go. Okay. All right, last problem. The Leaning Tower of Pisa. Over the years, that's why it's leaning, right? It's slowly been leaning further and further because the foundation, being set long ago, really wasn't properly designed to hold that type of weight. By the way, since this data set from the 70s and 80s, they've actually been correcting it, right? So if you go check it out now, it's not leaning as far as it was. They saved it. But anyway, there's my data. And there's a printout as well. So they gave me both. That's nice. And that's really the best case scenario because now I can plot the data, which is the first thing we should always do, and it's the first thing they asked me to do. And so I created, I got 2 extra lists in here to do this. And there's the plot. Okay, I definitely see a pretty strong relationship. Let's do a quick linear regression on it. Let's see. And that's what I thought might happen. Yeah, since I'm using lists that are labeled differently, it didn't want to work. But anyway, go ahead and clear yours out. Enter this into one of your like list 1, list 2s. Do the regression. Do your checks, right? So look at the residual plot. Make sure there's no pattern. Make sure there's no increasing or decreasing spread of the residuals, and then do a normal probability plot of the residuals to make sure that the y variable is responding normally to each change in x. Okay? All right. Describe the shape, strength, and direction. So I see what appears to be a pretty strong positive linear association. All right, letter B. The main purpose of the study is to estimate how fast the tower is tilting. What parameter in the regression model gives the rate at which the tilt is increasing? Okay, the parameter would be beta, the slope. Make sure you picked up that word parameter, beta. Okay, don't say B, right? B is the statistic, not the parameter. Okay, so that's a beta. Beta is the parameter for how fast the tower is tilting. That, by the way, is probably the most common mistake on the Chapter 14 test. Make sure you read carefully statistic versus parameter. So if it says, what's the parameter? Well, it's beta. I don't have that, right? A bunch of students report the statistic when it asks for the parameter. Well, it's this, that they're not the same, right? One's a statistic from data and one is an unknown true value. Okay, 99%, 95% confidence interval for this rate. How many degrees of freedom? Well, look at how many years we have. So let's see. And then subtract 2. And then the 95%. So this is 9 point whatever. Okay. And we've got to get our T star, 11 degrees of freedom. Somewhere I have, here we are. So 11 degrees of freedom, 95% is right there, so 2.8. 201. And the standard error of the coefficient. And there we go. There's our 95% confidence interval. You can go ahead and work that out. Make sure to write our conclusion. We are 95% confident. The true, I'm going to say rate of tilt is between 8.6 and 10.0, whatever units. Millimeter, tenth of a millimeters or something per year. Is that what it was? Yeah. Oh, tenth of a millimeter per year, yeah. Tenths of a millimeter per year. There we go. So that's problem set. Again, be careful. Make sure that you understand these confidence intervals, right? These are statistics, okay? These are estimating unknown parameters, right? These are not the parameters. And again, remember, when you do a confidence interval, what we're doing is we're saying if we collected data like this over and over and over again and calculated these confidence intervals over and over and over again from all those different data sets, 95% of the resulting intervals would capture beta in this case, the true rate of tilting. Okay. All right. Thanks for watching.